In this video, we're going to give a quick introduction to spectroscopy. Spectroscopy is a very important analytical instrumental technique that's used in experimental chemistry and experimental physics. Spectroscopy can be summed up by the term light-matter interactions. When light and matter interact, one of three things happens. Most of the time, nothing. This is something where we see if we have a matter over here and we have light coming in. In general, that light passes through the matter without any problem. Yes, sometimes the matter is opaque and it reflects back. We're not going to talk about that. But here we talk about transparency, meaning that the light and the matter have no interaction. Another possibility is that light is absorbed or that light is emitted. What does absorbed light look like? Well, if we have many different light waves coming through, perhaps some of them are stopped by the matter, and this is called absorption. Emission is a very similar thing, where the matter, which is in an excited state initially, starts giving off light and light is emitted. In both of these cases, absorption and emission, this happens because of resonance. Resonance is the idea that light, which has a frequency, nu of light, which we know is equal to speed of light over the wavelength of the light, when that frequency is equal to a frequency in the matter, we get resonance. What that means is that if the matter and light share a frequency, then they're able to interact, and the light is either absorbed or emitted. But if they are not resonant, so if we have the frequency of the light and it's not equal to the frequency of the matter, then nothing happens and it's transparent. So let's look at a few common spectroscopies. So infrared radiation, you've probably heard about this before. These are the heat lamps that you see in restaurants. What happens is the infrared light, which is low frequency, right? So this is low frequency light. This is resonant with the fundamental bond vibration frequency. So if I look at a molecule over here, let's say water, the vibrational frequencies of this water occur around 3,400 wave numbers. It's a frequency unit. And that's a pretty low frequency radiation, but yet it's resonant with water and as a result causes the bonds in water to vibrate. If we were to shine the same light on methane, nothing would happen because methane is resonant with light around 3,000 wave numbers. Okay, so that's infrared. Switching to microwave. Microwave radiation, again, is not going to cause bond vibration, but microwave radiation can cause molecular rotation. In most general chemistry classes, we look a lot at ultraviolet and visible light, and that's because this corresponds to the electronic transition. So these are the electrons in the molecules. Now, just for the sake of fun, we remember from physics the frequency of an oscillation is proportional to the square root of the strength of the bond holding, or the spring holding two things together, over the reduced mass of that bond or of that spring. So infrared, we're talking about mass of atoms, and for ultraviolet visible light, we're talking about electrons. So since electrons are much less massive, we should expect that the frequency would be much, much higher. And so we see ultraviolet light is a higher energy and higher frequency light than infrared light.